Now I would like to hand over the session
So should we
to
start?
Radhika Basgare ma'am. Over to you, Professor Radhika ma'am.
Sir, just
Yes, madam. Shall we start, ma'am?
Radhika ma'am, please wait. The recording will be started.
Okay, fine.
Yes, you can start now.
Okay, yes, ma'am. A very warm and pleasant evening to one and all present here. We welcome you all to our eighth session of 6 days online ATAL FTP, that is Quantum Computing Application Areas. I, Mrs. Radhika Pazhare, on behalf of Information Technology Department at AC Patil College of Engineering, Kharghar, welcomes our today's speaker, Mr. Amit Saxena, to the ATAL FTP on Next Gen Computing, Advances in HPC and Quantum Technologies for Data-Driven Insights. So, without further delay, allow me to introduce Mr. Amit Saxena, Scientist E at CDAC Pune, with over 18 years of expertise in AI, quantum technology, and HPC. He has led critical projects like ParamQ, which is India's superconducting based quantum computer, and AgriHub, an innovation hub for agriculture. As a part of the National Quantum Mission, he is advancing quantum computing research and applications. He is also a member of the BIS Standardization Committee, and he has published papers in reputed journals like Nature Scientific Reports.
So yeah, am I audible?
Yes, sir. Can you please wait a while?
Yeah, should I share my slides?
Uh, we welcome you, sir. Please accept our virtual token of respect. Now I request Mr. Saxena, sir, to start the session. Over to you, sir.
Thank you so much, ma'am. A very good evening, and I think it's a very long late night session, and I will try to make it as interesting as possible, and I will also try to make it as light as possible because you know that quantum computing is itself is a very like new area, and a lot of new thinking is required. I think as Shashank, my colleague, he was saying that we have to totally rethink when we are doing the quantum computing. So let me share my screen. Yeah. So are my slides visible? Yeah. So should I start?
yes, sir.
Okay. Good. Thank you. So today, I think we will be talking about quantum computing application areas. When we see recently, I think you all have heard about the news about Google. So it's making a lot of news, and it's showing that whatever work it took a long time and it can be done in 5 minutes. So all sort of things are there in the quantum. So daily we hear a lot of new news that some sort of new benchmark is there or some sort of new uh, application is there, and then they have quantum has shown the advantage over this classical, and whatever the classical can do in so many years, the quantum can do in like some minutes or some seconds. Okay. So when we talk about this news, and when we talk about this area, so let us go inside, deep inside this particular area, and let us see ourselves that where are we and where are we moving, and what is the future prospect of this quantum computing application areas. Okay, so let us start. So first of all, let us see why we need the quantum computing. Okay, so quantum computing, you can see, you can name a company and that company is working on quantum computing. You can see IBM, they are leading in the quantum computing. They have got to 1000 qubit chip. Then we see Google, it is also in quantum computing. Microsoft, it is also in quantum computing. So all the big companies you can see, or even in fact every company is there in quantum computing. So why we need quantum computing? Because to keep India in the next frontier technology advantage of quantum computing, and with exponential problem solving potential, which can directly impact our country's socio-economic and financial security concerns. When we say financial and security concerns, it is very important. Why every country is spending so much amount on this quantum computing? I can give you one example. The requirement, like all of us are using this UPI, all of us using banking, and quantum computer has theoretically shown a potential where if we have enough number of qubits, then they can break this RSA encryption codes, and that means the total financial system of any country can collapse. Okay, so this has so much danger, and then we have this post quantum cryptography and those type of features. But seeing this, it is a very strategic application, and then a lot of defense and security concerns are there with this quantum computing. So based on that, I think it shows that there is a need of quantum computing. That's why our country has announced national quantum mission. We'll see this. So we'll start with the computing basics. So when we say what is computing, so you can go with the era of abacus. All of you know that it started from this abacus computing, where you can call it as a like first computer, where something was used to compute. Okay, so generally when we see abacus, it's a counting frame, and it was used in ancient Europe, China, Russia, and then Hindu. It's before the adoption of Hindu-Arabic numerical system. Okay, so the exact origin of abacus is not yet emerged, but yeah, generally we can also see these roots in our country. Okay. Then this Turing machine. So Turing machine, as we all know, it was named after Alan Turing, the famous mathematician, and then it is based on the recursive enumerable languages, okay, like type 0 grammar. So this Turing machine is the base of every computing element. Okay, so this is the basis computer. So every computing machine has to pass the Turing test. Okay, the Turing test is like that. Yeah, it fits in a Turing machine framework. Then came the age of the transistors. It changed everything. So the transistor, when it came, it shows a new computation paradigm. And now whatever system you see, all the computers, they are based on the transistors. Okay, in between there are some vacuum tubes and those type of systems. Then come this microprocessor. So microprocessor, you can know this Intel 4004. So this was a 4-bit central processing unit used by the Intel in 1971. And it changed the scenario. Totally it changed the scenario. And it also changed the computational scenario. Okay. Then came our personal computer. Like you can see IBM personal computer was there, Apple was there. So all these systems, when we say personal computer, they are based on von Neumann architecture. Von Neumann architecture, we all know that's a memory unit, control unit, ALU, and then input output. Okay, it's a very simple architecture, and all our this desktop PCs, yeah, all our this desktop PCs and everything is based on this type of architecture. Okay, then comes the Moore's law. Moore's law says that the transistor of every chip, it doubles in every 1.5 or 2 year doubles. Okay, but when we see this Moore's law, is it really true nowadays? Okay, so the thing is that what we are doing actually, we are keep on decreasing the transistor size, and we are keep on increasing this uh, chips. So whatever transistor number of transistor, we are keep on increasing in the chip. The moment the number of transistor are increasing, so definitely its computation power is going to increase. Okay, so based on that, it's not actually a law, it's actually what we can say, a observation that this is happening. So we keep on increasing the computing power and increasing number of size of transistor. But the problem is actually we cannot increase the transistor after a certain level. Okay. So based on that, there came a concept of parallelism. Okay. When we call a parallelism in hardware as well in software, it means we can do two simultaneous tasks parallelly. Parallelly means uh, if we can one task can be done by one person, then we can appoint two person. So those two person can, and we divide the tasks parallelly between the two. The important condition is there that the task should be separable. Separable means those two people should not interfere with each other. There should be not much communication. Then only these two tasks can be done parallelly. So that's the question of parallelism, where there is a master node, there is a compute node, and all the compute node, they are working parallelly, and they are doing independent tasks. Independent tasks means there is no much requirement of this task to communicate with each other. And even if there is some communication, that should be like minimal. Otherwise, the parallelism will not be giving the full potential of whatever speed up we want to gain. Okay. So all these things are being described by the Flens classification: simple instruction, single instruction, single data set; multi instruction, multi data set; single instruction, multi data set; multi instruction, multi data. These are the four type of parallel architecture we given classification given by Flens. Okay. So this we know that this is the basis of the parallelism. Okay. So why we are talking about this parallelism? Because all our supercomputers that we have, so you know that CDAC is known for its supercomputer, and this is the diagram of the first Param supercomputer, Param 8000, that were released in 1991. And all these supercomputers are based on this parallel architecture. Means there are different number of nodes. Earlier it was based on transmitters. So all these nodes are there, and these nodes can do parallel processing. And based on this parallel processing, all the parallel computation tasks are being executed. Okay. So in November 87, CDAC was formed, and we were formed for this mission of first supercomputer in our country. And Dr. Vijay Bhatkar, all of you may knowing. So he established this first Param supercomputer, and CDAC was established for this. And then we had Param 8000. And why this? What this Param? What was so new about this Param actually? Since all the supercomputer in US, they were using different type of architecture like vector supercomputer, mainframe. But when we see Param, we introduce a new architecture called as cluster computing. Cluster computing means there are many different nodes of like less capacity, but they work together in parallelism, and then finally they can beat a big mainframe and vectors. Nowadays, you can see this vector supercomputer, this company called Cray, that is not there right now. It has been like absorbed by HP. Mainframe systems are also gone. Okay, there are some old legacy systems available, but they are not there right now. All the supercomputers, they are based on this architecture, which Param followed at that time. Okay, so that is known as cluster architecture. So under the National Supercomputing Mission, we are having different Param supercomputers. So you can see under NSM, various supercomputers are being installed everywhere across the country. Param Shivaya, Param Shakti, Param Brahma. So these are all the supercomputers that are installed across the country. Then there is a Param Utkarsh, Param Ganga, and finally you can see Param Eravat, that is at CDAC Pune. Okay, so this is the number one supercomputer in our country right now, available at CDAC Pune. And Param Siddhi was there. Param Siddhi and Param Eravat, actually they are now connected with each other. So with this computational, with this parallel computing and this supercomputing background, we are moving to the quantum computing. Okay. So this quantum computing, when we see, there are majorly four focus areas. One is quantum mechanics, that is backend or background of this quantum computation. Then there is a quantum mathematics, and there are quantum algorithm and quantum simulators that are being used. Okay. So we'll be talking about these areas. When we see quantum technology as such, it is quantum is like not only in computing. So we have quantum in communication, we have quantum in metrology and sensing, we have quantum in quantum materials. Okay. So when we say quantum technology, then we have computing, communication, metrology, and materials. Okay. And then we focus on quantum computing. Okay. So when we say brief history of quantum computing, it was 1982, Richard Feynman proposed that quantum mechanics phenomena can be used for the computation. And that changed the scenario totally. And theoretically, it was conceptualized that this quantum computation can be used quantum mechanics can be used for the computation phenomena. Okay, and then 1985, Richard David Deutsch he developed a quantum Turing machine, and 1994 Peter Shor came with the quantum algorithm for factoring, and then 97 Love Grover developed a quantum search algorithm. Okay, so everywhere you can find one Indian origin person. So Love Grover is also Indian origin person, so who developed a Grover algorithm that is very popular, very famous quantum algorithm. So when we talk about Moore's law, so we said that Moore's law is failing. Now the exact reason of Moore's law failing is actually the quantum mechanics. Why? Because when we see Moore's law, the transistors, we are reducing the size. Now how the size is reduced? Because the length, it is like PNP. So the length of this particular area is being decreased. Okay, this length cannot be further decreased because the moment this gate, there is a potential here. Okay, so electron flows from here to here, and once we apply the potential, this stops the flow of electron from here to here. Okay, and that behaves as a switch. So if we apply the potential, then electron can't flow. If we don't apply the potential, the electron can't flow. So it is acting like a switch. It is 1-0. Okay, but what is happening? The moment this size is being reduced, electron will show a tunneling effect. Tunneling effect means even if potential is applied, it will cross it. So there is a distance. Okay, there is a distance of that particular nanometer where this particular length cannot be decreased further. And if this length cannot be decreased further, it means transistor size cannot be reduced further. It means the transistor size cannot be reduced further. It means the chip size cannot be reduced further, and the capacity of chip cannot be increased further. So based on that, there is an end of Moore's law based on this reducing of transistor size. Now what to do once the Moore's law is ending? So we have to find alternative methods because the computation requirement is increasing. So we have to find various computation methods. So one of that is quantum computing. Okay, there are various other areas which people are working, like there is a biological computers also there, and there are various genetic computers. Those type of computers are also being explored. But this quantum computer is a reality now. You can see this is the IBM quantum computer, and this is how the quantum computer looks like. Okay, so major part of this quantum computer is actually cooling, because we have to cool a chip to superconducting based temperature. And superconducting, you all know, it's near to 0 degree Kelvin, and not exactly 0 degree Kelvin, but it's like 5 millikelvin type of temperature is being maintained. And you can see there is a helium gas flow, and based on that helium gas flow, this particular chip, there is a chamber. This chamber is there, and below the chamber there is a like we can say quantum processing unit. We call it QPU. So in classical there is a CPU, but in quantum there is a QPU. So based on this QPU, this particular cooling is being provided to this QPU. Okay. So this is how a quantum computer looks like, and I have been fortunate to see this quantum computer at IQM Labs, Finland. So this is where we can see. Now you can see if we open this container, so there is a very beautiful chandelier type of thing, okay, which is showing various plates. Now these plates represent a temperature. So it is like 10 Kelvin, 5 Kelvin. Okay, then it becomes millikelvin. Here at the bottom, there is a quantum process unit QPU. And there is a helium gas flow from here to here, where it particularly at this level, it produces like 5 millikelvin temperature, which is near to superconducting temperature. And why superconducting temperature required? Because this is a superconducting based QPU. Okay, so that's why the superconducting temperature is being required. So it is very similar. You can see this quantum computer is very similar to the first like classical computer ENIAC. It is a big size, and it was like based on the vacuum tubes and those type of things. So this is very similar. But now you can see as the time will increase, this quantum computer will become very small in size, and it will be like available in the form of a desktop type of things. Okay, because a lot of technology is being explored for this quantum computing. So what are the basics of this quantum computing? Is superposition, entanglement, and quantum tunneling. Okay, these are the basics of the quantum computing. So we all know that superposition, entanglement, and tunneling. So when we say superposition means that if a physical system,
Excuse me, sir.
yeah.
Sir, are you changing your screen, sir? I think it is tick now. It is only first screen is showing right now.
Oh, that's what I asked you.
Yeah, now it is visible. Thank you, sir.
Yeah. So let me again rewind it. So we started with need of quantum computing. We started with the abacus, and then we talk about Turing machine. Then we talk about transistors. Okay,
Yes.
and then
Yes,
we
sir.
talk about the microprocessor.
Yes.
Then we talk about personal computer. Then we talk about von Neumann architecture, Moore's law, and parallelism. Then how the parallelism is being represented by this master node and compute node. And this is the Flan's classification, SIST, SISD, MISD. Then we talk about Param supercomputers. These are the first Param supercomputer, Param 8000, and in the right you can see Param 10,000. Okay. Then this Param supercomputer, you can see this was developed by CDAC in 1987. CDAC was formed, and Dr. Vijay Bhatkar, he made this first Param supercomputer along with his team, and there are many members of this team still working in the CDAC, and we are proud of this team. And then this is based on cluster computing. Cluster computing, actually, when we see a lot of computers, they were based on mainframe and vector. But Param used the cluster computing where multiple nodes parallelly work together to solve a particular task. And these are the various supercomputers installed on the National Supercomputing Mission across the country. And there are 70 such installation to be done under National Supercomputing Mission, which CDAC has taken. And you can see the Param Airavat, that is the last, it is CDAC Pune. This is the number one supercomputer in our country. And along with Param Siddhi and Param Airavat, we have like combined it. It is AI based system. So it is having GPU also. So when we talk about this quantum computing, there are quantum mechanics, mathematics, algorithms, simulators. These are the various quantum technologies, computing, communication, metrology, sensing, and materials. And this is a brief history where Richard Feynman proposed quantum mechanics can be used for quantum computing. And then why Moore's law is failing? Because there is a PNP diode, and then finally what is happening, whenever whatever potential we are applying at this place, this potential, we cannot reduce this particular size. The moment the electron will flow from here to this, it will tunnel. The tunneling is one phenomena which we have already seen. So based on this, the quantum computer looks like this. So this is the IBM quantum computer. The majority of this quantum computing, these things are actually, when we see majority of the quantum computing is actually cooling. And this cooling is being provided by the liquid helium. And this, I was fortunate to see this quantum computer in real at the IQM labs in the Finland. Okay, so what we can see here, actually, this is like big chandelier type of thing where from Kelvin to millikelvin temperature. So here at the basement, at the top, at the bottom, there is a QPU. QPU is quantum processing unit, and the top it is like Kelvin temperature, and from Kelvin temperature to millikelvin temperature it is being reached. And finally, the quantum chip is superconducting based chip, so it is working at a very 0 degree Kelvin, we can say by standard theoretically, but it works on the 5 millikelvin type of temperature. Because it is based on superconducting based architecture. So it looks similar to the very old classical computer. It was very big, like a room, and the quantum computer there. So this quantum computing is based on superposition, entanglement, and tunneling. And where superposition means a physical system may be in one or many configuration, the most general state. And quantum tunneling is a quantum mechanical phenomenon where a particle passes through a potential barrier classically cannot surmount. Okay. And quantum entanglement is quantum states of two or more objects have to be described in reference to each other, even though the individual object may be spatially separated. Let us understand what is these three phenomena. When we say superposition means okay, what is superposition? So let us understand it by one very basic example is that suppose you have a coin. Okay, the coin is either head or tail, but when the coin you are tossing, the coin is in the air. So that coin, when the coin is in air, whether it is head or whether it is tail, so neither it is head nor tail, we can call it is represented as a superposition state, where neither it is one, nor it is zero, neither it is head nor it is tail, but it is a in a superposition state where we cannot say that it is head or tail. The moment it falls down on the ground, we can see head or tail. Similar phenomena is like this quantum, okay, superposition, where it is a particular object in a state of 0 or 1, but we don't know. The moment we observe it, it comes in the 0 or 1 state. Tunneling, we have already seen. In the tunneling, you can see this example. What is a tunnel? There is a big mountain. Okay. Now you have to climb the mountain and you can reach there. Okay. What if I make a tunnel? So the electron can pass from this tunnel. Okay, so it does not need to cross the potential by moving up and down. It can directly pass it. Okay, so this phenomena is possible because there is a wave nature of the electron. So every mass at the subatomic level, it can show a wave nature. That's why being a wave, it can pass on through this known as a tunneling phenomena. Then the entanglement. Entanglement means there are two particles and they are entangled. Okay, now whatever distance I can take them away, the moment I change the state of one particle, the state of another particle automatically changes. And Einstein called it a spooky action at a distance. Okay, so he was not able to believe this type of phenomenon. But quantum mechanics is a very weird phenomena. But the most accurate theory at this time is quantum mechanics theory. Okay, there is not even a single instance that quantum mechanics theory failed. Newton law, they can fail, and even Einstein theory failed. But finally, quantum mechanics is the most stable. Till now, it has not failed in any instance. Okay, so let us understand this. There is a double slit experiment where uh, if we fire an electron, it can either pass through this slit or it can pass through this slit. But generally, what happens? It should show either two bands. It should show two bands. But experimentally, if we do it, we will see a interference pattern like a wave. But electron is not a wave. We don't study electron as a wave. Then how it is making a wave pattern? So that is how it is a quantum mechanical phenomena where these particles can behave as a wave. They can interfere with each other, or they can even interfere with itself, and finally forming an interference pattern, just like a wave. Okay. So if you are not observing it, it is a wave. If you are observing it, it is particle. Wave and particle. Okay. So mere observation can change the state of this particular particle. So it is a wave, but that is a very special wave that is known as probability wave. It is a probability wave. So if you want to calculate a probability of the particle, the wherever the probability is maximum, you can find the particle there. Okay. So this is how we can calculate. So if we understand classical bit versus qubit, so classical bit generally represented as 0 and 1. And when we say qubit, it is represented as a quantum bit. It is neither 0 nor 1, but it is in a superposition state. This we have already seen. Now let us move to this problems. Okay, why we are taking all these supercomputers? Why there is a quantum computer requirement? Why there is a desktop PC requirement? Why there is CPU? All this. Why we require all this? Because we want to solve some mathematical problem. We want to solve some sort of problem. And what are those problems? Okay, let us imagine what is the problem. Let us say one of the problem is like there is a person who is a salesman. Okay, the salesman want to travel various cities to sell a product. Okay? And that travel route should be minimum, because with the minimum expenditure, the person need to travel more and more number of cities. So this is basically an optimization problem, and that is known as a very popular problem known as traveling salesman. So we now, if we see it like this way, it seems very easy. But let us see in this age, there is a big airline. That airline want to optimize its flight routes. Then this problem become a very expensive problem, because aircraft, they are like using this fuel, and that fuel nowadays, this carbon footprint and everything is there. So there is a lot of effort to reduce the carbon footprint, and lot of effort to reduce the cost of that travel, so that the profit margin increases of that particular airlines. So if a particular airline has a very optimized route, okay, then it can do a lot of change and a lot of profit margin it can increase. So it's a big money value problem. Okay, it's not like a academic problem where traveling salesman you can solve. It's real practical solution. Can help any airline, or can help any, like there is a Uber or this Ola, so they can also use the optimization algorithm. So which driver we need to send based on the optimization things. Okay, so optimization is actually a very important aspect, and lot of companies, they are spending a lot of money on optimization efforts. Okay. So we can solve this problem. So there are problems. So we can divide the problem in different categories. So there is a problem that can be solved in polynomial time. Polynomial time is any polynomial like x and those type of things. And so like sorting and searching, okay, these problem can be solved in any polynomial time. Sorting and searching. So sorting means if you want to sort any number from ascending or descending order. Searching means if you want to find any number. So this is a problem known as P class problem, polynomial class problem. The problem which cannot be solved in polynomial time but can be verified in polynomial time is called non-deterministic polynomial. It is NP class problem. Okay. So like Sudoku, prime factor, traveling salesman, these all are the class. So finally we have all the NP problems. Actually, this P problem are a subset of NP problem. Okay. Now P class easy to solve and easy to verify. NP class is hard to solve and easy to verify. Okay. So if P is equal to NP, if P is equal to NP, it means what happened? Then there is an online security and vulnerability to attack. And then finally, if P is not equal to NP, then there will be definitely be some problem that cannot be solved. Okay. So this is a very big question. And this is so big that there is a $1 million award for this. Either you prove P is equal to NP or you prove P is not equal to NP. P is equal to NP means this set. This P set is equal to NP set, or if P set is not equal to NP set. Okay. So if it is not equal, then there is always some problem that cannot be solved. So based on that, it is a $1 million question. Okay. Until that it is not proved, whether P is equal to NP or it is not equal to NP. So reduction means a problem A reduces a problem B if there is a way to solve the problem A using deterministic algorithm to solve the problem B in polynomial time. Okay. So this is known as reduction of the problem in polynomial time to another problem. Okay. So what is this NP hard? If this particular problem is, if a problem is NP hard, if every problem in NP can be polynomially reduced to it. Okay. So there is another set is called as NP hard. If we can polynomial in a polynomial time, we can reduce one problem to another problem. So that's how it is known as NP hard. And NP complete is actually a problem is NP complete if it is NP and NP hard. So it is a, what we can say, cross section of this NP and NP hard problem. Okay. So based on this, we can classify the problem in computation complexity basis. There is a P class problem, there is an NP class problem, and NP class again, it is NP hard or NP complete. Okay. This is very easy classification. Now, when we say NP complete are basically decision problem and NP hard are actually optimization problem. So based on this problem classification scenario is very clear. There are NP problem. First of all, there is a polynomial problem. This is very easy to solve, very easy to verify. There is an NP problem which is hard to solve. Then there is an NP hard problem, and based on the NP hard and this intersection of this NP hard and NP, it is a NP complete problem. Okay. So let us again come back to traveling salesman. So traveling salesman problem is actually, we can say it's an NP hard problem. And suppose a salesman has to travel to all the path, then it has to cover optimized way. It has to cover in optimized way all these paths. Now, why we are discussing these things in a quantum computing part? Okay, we will see it afterward, that how quantum computer has a capability which can solve this sort of problems. Okay, so let us see how quantum computer works. I think you might have heard a lot of lectures about quantum gates. So I think I will not go much in detail because these are very basic. Like there is a classical gates when we say NOT gate, AND gate. There's a classical, and similarly there are quantum gates. Okay, and the quantum gate are actually, they must be reversible. Okay, so they act on a qubit instead of classical bit. The quantum logical gate are represented by unitary matrices, and the number of qubits in the input and output of gate must be equal. So there are various gates. Okay, so this is a poly X, poly Y, and Hadamard gate, phase gate. So this is all CNOT gate. So what is a quantum algorithm? Actually, a combination of all these circuits, all these gates to form a quantum circuit. So quantum algorithm is actually nothing but a quantum circuit, which is a combination of quantum gates, and quantum algorithm work by applying quantum operation in form of quantum gates on qubits. So this is qubits, these are gates, and finally this is known as a quantum algorithm. Okay, and finally all these things will be processed at the quantum processing unit. Okay, this is the definition. Now quantum algorithm, we can either execute on a quantum computer or we can execute on a simulator. Okay, what is simulator? Simulator is actually a classical supercomputer or a classical computer on which the quantum phenomena can be simulated. But there are limitations of it. We cannot simulate a very big problem on a simulator. Okay, but still we can learn. So when we say quantum simulator, it is HPC implementation to execute mathematical model of quantum computer. Let us see. Suppose there is a Hadamard gate. The Hadamard gate is actually nothing but this is a qubit. It will define the equal probability distribution. Okay, equal probability. Equal probability means 1 by root 2, 1 by root 2. So finally, this is applied in this qubit 1, 0. Finally, when we apply it, we will give the answer 1 by root 2 as an equal probability state. Now 1 by root 2 square is equal to 1 by 2. It means this is a probability is actually 1 by 2. And when we say 1 by 2 plus 1 by 2 is 1. So sum of probability is always 1. Okay. So all the gate operation actually vector operation. Okay. So like C0 gate is having these matrices. Hadamard gate is having these matrices. Finally, we do all this matrix operation. We will finally get all this matrix format. Now we have to find the like crucial product of this particular matrices. Okay, and then we find the final answer in that way. But all this phenomena has to be matrix multiplication. Whatever the matrix multiplication, we have to implement on a classical supercomputer. Okay, and the problem is actually the moment we increase the number of qubit, this dimension of these matrices, they become 2 to the power n. So the moment we increase one qubit, it becomes exponentially increasing. So this exponential increasing, so that a matrix, if it is exponentially increasing, it requires a lot of RAM in the system, classical system. So after maybe 30 qubit or maybe 35 qubit, it will become really impossible to execute this particular type of quantum phenomena on a quantum simulator. So that's why we require a real quantum computer for that. You can see this. The moment we increase the number of qubit, it becomes exponentially and drastically increasing. And this can be understood by a simple phenomena. What is the exponential increase? Let us take a chessboard. Okay. Now we apply one rice on the first chessboard block, double it on the second, double it on the third, double it on the fourth. The moment we reach 64, we will require over 18 quintillion grains. 18 quintillion grains. Okay. That is huge quantity. So that is the power of exponential. Okay. Now, where this parallelism come in the quantum computing? We were talking about the traveling salesman. Okay. Let us understand with a very simple example. So there are about 2 to the power n states. Now, a traveling salesman means if I want to go from one city to another city, I have to travel each and every city. So I will go from first city, second city, third city, fourth city. All I have to do in a sequential way, one by one. Okay. So then I have to complete 2 to the power n states. Okay. 2 to the power n states means I have to complete all these one by one, all computation I have to take care. But when we say quantum, what is happening? I make a superposition state of all this path and finally I observe it. The moment I observe it, I will get a probability that, yeah, that salesman should travel to this path and this path is a higher probability path. It means that path is the shortest path. Okay. With a more probability to travel. Whenever there is a probability, there is always, it cannot be always correct. Okay. So the probability is 75%. It means 25% it will be wrong. 75% it will be correct. So for that we have to measure any probabilistic thing, we have to execute it many times, maybe 100 times. So if we execute 100 times, then 75 times I will get correct answer, 25 times I will get wrong answer. Okay. So that's why all quantum computing phenomena are actually probabilistic. They are not deterministic. So it is all probabilistic. So wherever this probability is there, we have to use. Now let us see a simple example. There is a 2 qubit. Now with the 2 qubit, how many states can be there? 0, 0, 0, 1, 1, 0, 1, 1. Okay. Now if my answer is actually, I want to get my answer. So I am running this computation 100 times. So 50 times I am getting 0, 1, 17 times I am getting 0, 1, 0, and 33 times I am getting 1, 1. So what is the answer? The answer will be whatever answer we are getting, highest probability. The highest probability here is 50 times. So 50 times the correct answer will be 0, 1. So that is given by the probability. Okay. So let us understand this by a geometrical representation of this particular qubits. Okay. So whenever we say in an atom there are various orbits, So if we call it as a states, so it can be either 0 state or it can be 1 state. Now when we say this arrow, so this is known as Dirac. We will see it afterward. So let us see, there is 0 state and there is a 1 state. I represent 0 state at the x-axis and I represent 1 state at the y-axis. And there is any superposition state in between that. So let us represent it by psi. And if I project this vector, so this is radius equal to 1, so this is a unitary vector. So if I project this vector here, alpha is actually the projection. So the alpha is the projection on x-axis and beta is the projection on y-axis. And we don't call it x-axis, y-axis, we call it basis. It is 0 and 1. Okay. Now what is 0 is actually represented by the form of 1, 0 as a vector, and 1 is represented in the form of 0, 1. And psi will represent by alpha and beta. And how to represent psi is equal to alpha and 0 and beta and 1. Now let us see what is important. So the superposition state is represented in a ket state. Okay, this arrow is actually ket state. And if you reverse it, it becomes bra state. So bra and ket. So where alpha and beta are the complex probability amplitude of the qubit, we determine the probability of measuring 0 and 1. So finally, alpha square modulo will give us the probability of the state 0. And beta square will give the probability of the state 1. So whichever is more. So finally, what is the final state of our system? Whichever probability is more will give the correct answer. Okay. So if alpha is more, then our answer will be 0. If beta is more, then our answer, suppose if I measure 100 times, 75 times I get beta and 25 times I get alpha. Okay. 75 times I get 1 and 25 times I get 0. Okay. So the probability is defined by the beta and alpha. Okay. So finally, answer will be whichever probability is more will be the correct answer. And the sum of probability is always 1. That's why alpha square beta square is 1. Now there is various methods to implement the qubits. Okay. There is superconducting qubits. There is a semiconductor qubit, there is a trapped ion qubit, there is a photonic qubit, there is a defect-based qubit, topological, various ways of implementing qubit. The most popular one is right now superconducting based qubit. So there is a material like niobium which exhibits zero electric resistance. So this superconducting based qubit, whatever we are seeing is represented in this way. It is represented in the form of Josephson junction. And all these superconducting based systems like which we have seen, they require low temperature like superconducting based temperatures. Okay. And then there is semiconductor material like silicon and gallium arsenide. Then ions are there for the trapped ion. Then photonics are there which use photons. Then there is a defect based NP diamond where NV center diamond is being used for the nitrogen vacancy for the qubit calculation. And there is a topological nano wire qubits. Okay. And then there is an interaction between magnetic property and so there is a NMR based qubit representation. Now, when we talk about superconducting based chips, the highest number of qubit are being shown by the IBM. So it's like 1000 qubit. And Google is also there. Intel was also there with 14 qubit. But in our country, TIFR lab is there, which has made this 7 qubit chip. Okay. So it is right now 6 qubit are working. So there is a 7 qubit chip where 1 qubit is not there. So 6 qubit are actually finally we are having in India. So based on that, our National Quantum Mission was established, which was announced on 19th April 23. Cabinet approval was there on 19. It was announced in 2020, and cabinet approval was given on 19th April 23 with a total cost of 6,000 crores from 2023 to 2030. And there are various hubs recently formed: computing hub, communication hub. So computing hub is IISc, communication is IIT Madras. So a lot of all the institutes are being formed as a hub, and under that hub there are like various projects will be executed. Okay. So based on that, we can see the quantum market is growing. A lot of companies are growing. There is a huge investment from every country in this quantum computing area. So quantum technology in India is also growing as per the NESCOM survey. And this National Quantum Mission is based on these 4 hubs. And the major task is actually of these hubs actually is to make a 50 to 100 qubit was the target, but now it has been increased because we have to go to multiple hundreds of qubits development under this national quantum mission, as well as we have to do communication, we have to do materials, we have to do a lot of things. So it is a quantum technology mission. It is not a quantum computing mission. Okay, so it is covering every aspect of the quantum in this our mission. Okay, so let us come to these applications. Okay, so why we are talking so much about the quantum computing? Because a lot of potential is there in the application area. When we talk about artificial intelligence is like a big buzzword now. You can see a lot of LLM model being developed, a lot of artificial intelligence being used in every field, each and every field artificial intelligence being used. So based on that, quantum computer can empower the machine by learning, enabling AI program. So quantum and AI can work together to give a more efficient AI based algorithms. Then there are problem like drug discovery. We all know that there was recently a COVID era, and still now there is no drug for the COVID. Okay, there is no medicine for COVID. There is vaccine, but there is no medicine for the COVID. Okay, so a lot of research is being going on with this development of this COVID vaccine and COVID medicine. But the problem is actually the competition is very huge. There are millions of drug targets, and this COVID uh, inhibitor and all those things we have to dock it. So docking and those studies, it require a huge competition power, where the quantum computing can definitely show a lot of advantage in these aspects. As we discussed optimization problem, where we have to calculate the optimized solution on a particular space. So definitely this is also a very it can we can say it is an NP hard problem. So based on this optimization thing, quantum computer can definitely provide a very good advantage on this optimization. Then there are cryptography application. Cryptography is actually we are sending some information from one place to another place. It is being encrypted. That encrypted information is being transferred in the form of cryptography. Now quantum computer has the capacity to break this particular cryptography code, and definitely theoretically it is there. Right now we are in noisy intermediate scale computing NISQ era. The moment we have logical qubit, definitely then this type of threats are there from the quantum computer, and there is a post quantum cryptography also there. Financial services. Now the financial services are there. You can know share market. Lot of companies they are every company is opening a quantum computing unit. Okay, lot of big companies which are dealing with financial, they are having a quantum unit where they are using quantum computing to finally calculate the portfolio optimization, to calculate the share market trends. So these type of efforts are being done in the like there is a company called JP Morgan which is having its quantum unit established inside it. Okay. So now to execute all these algorithms, all these applications, we need some platform. And right now in India, right now we have a 6 qubit quantum computer which will be released soon in December by DRDO, TIFR, and TCS. But we need a more like we can say user friendly interface. You can see the CDAC along with ISC and IIT Roorkee, we have developed a simulator platform, and you all can access it by using qctoolkit.in. Using your Gmail account, you can log in. You can directly execute these algorithms on there. There are examples given there. There are a lot of material there and a lot of examples there. You can just go there, execute there. At the backend, it is running on a supercomputer. Our Param supercomputer are being used at the backend, and it is accessible freely. It is for the students. It is for the researcher, and you can use it and you can execute a lot of algorithms on this. So this is the first Indian, we can say, simulator platform available for the Indian researchers, and lot of algorithm execution can be done. So this QSIM was developed in launched in 2021 by our honorable MOS that time. We also have a simulator called ATAL simulator, which is like a 35 qubit simulator that is with CDAC. So we can see that we have factorized a 5-digit number. So factorization is actually Shor algorithm is actually for a prime number factorization, and prime number factorization plays a very important role in this encryption and technology. So these prime numbers, we were able to demonstrate a 5-digit prime number factorization by using this particular code in this machine. Okay. So then there are like various, we can say, so these are the platforms. Okay, so we were talking about all these applications. We have applications in the artificial intelligence. We have problems like drug discovery problem, where we have seen the COVID era. Then there is optimization problem. There is cryptography problem. There is a financial service problem, and there are lot of problems. And every problem cannot be solved by quantum computer. Okay, so quantum computer is not good for doing arithmetic operation 2 plus 3 and those type of things. Their classical is the best, but quantum computer is mostly good at the optimization problems. Okay, or solving the optimization problem. So based on that, these problems we need some platform where we can execute these particular problems and we can solve this problem. So this QSIM is one of the platform which you can use, and ATOS is another, but this ATOS is being used privately by today. Now let us move to the AI based things. Okay, AI applications. So we generally know that AI and quantum computing can work together. And right now what we are seeing is actually quantum feature maps. So quantum feature maps are the quantum circuits which are designed to encode classical data in quantum state. They transform the classical data point into quantum state that are designed to high dimensional Hilbert space. Now what is a Hilbert space? A Hilbert space is nothing but a complex number space, infinite dimensional. Okay, it's a infinite dimensional complex number space, and all this quantum computing data is actually complex number. Okay, and in these quantum feature maps, they can be tailored into specific data set and classification task. Okay, so what is happening? There are a lot of features in the classical part. We are mapping all those features to Hilbert space, which is like a multi-dimension space when we say in this particular thing. So this mapping helps a lot to understand this quantum data, and finally, even with there are some paper which can say that even with the less number of features, we can predict very good result by using this quantum approach. Okay, so this quantum convolutional neural network for the medical image classification, that we have published, one of the student that she worked on this. So investing the quantum convolutional network for the image classification and exploring quantum computing potential for classifying the image data, even though with a very limited feature, but we can do it. So application of QAnon, distinguishing between normal and pneumonia cases using chest X-ray over them, and this demonstrate the QCNN effectiveness in classifying the image, and considering the paradigm shift in the data intensive challenge, data intensive challenges with the advent of the quantum computing. Okay, so we are seeing a lot of potential of quantum computing, but right now the accuracy and those number of quantum computer are not so good. Okay, generally when we see till now, the classical approach is still better in the AI and this thing, but yeah, quantum has a lot of potential. Now why I am saying this, because right now this quantum computer, they are like not fault tolerant. They are not working logically, but they are like noisy intermediate scale quantum computing. That's why there is no like real advantage that is being shown by this quantum. The moment we have a fault tolerant quantum computer, the scenario will drastically change, and finally we'll see a lot of quantum advantage, and you will see a scenario changing where these algorithms, optimized algorithm will be executing, and a lot of problem can be solved in the real time. Okay. So this is how actually this leveraging quantum parallelism QCNN was there used, and then this has a potential, theoretically it has a potential to surpass the classical counterpart, but there is a limitation of the logical number of qubits. Okay. And there is another like paper which we can see the pancreatic data classification with quantum machine learning, where we can see that normal classical and quantum. So yeah, we can see very little difference. So quantum is right now comparable with the classical in terms of accuracy, but it's still very bad accuracy. But yeah, we can see that a lot of these methods can be tried. And once we are quantum ready, once we have this quantum computer available with logical qubits, definitely drastically it can change the scenario, and we will definitely get a quantum advantage. Now there is another platform which we are developing is actually other than simulator, is actually quantum accelerator. Okay. Now when we talk about this particular platform, okay, so what we are doing, we are taking the simulator and we are scaling it up. Okay. So what is happening is actually this simulator takes a lot of time where we are executing on CPU. Okay. So if you use GPU, if you use vector, if you use FPGA card, all these are known as accelerator cards in HPC. Can we decrease the time of execution? And definitely we have seen we are getting more number of qubits, like in GPU we are getting 30 qubits, in vector we are getting 18 qubits, FPGA we are getting 24 qubits. So that sort of things is we are trying. Can we reduce the computation time? Definitely yes. This particular accelerator card, because all the operation in the quantum circuit is, as you see, is our matrix multiplication. Okay. So if we are having a matrix multiplication scenario, and all these cards are actually very good in this particular type of workloads. So definitely we will see a quantum accelerator advantage in scaling up these particular efforts. So the simulator can be used by up to 30 qubits. Can like 40 to 41 qubits. It has been observed, and but beyond that, it is right not possible, because for increasing 1 qubit, we have to double the number of nodes. Okay, and that become very expensive because it's all exponential to the power. So what we have done, we have developed 3 test bed, one GPU test bed, one vector test bed, one FPGA test bed, and we have integrated with our supercomputers. Now this platform is being used for execution of applications, execution of the quantum applications. This particular platform is being used, which enhance the simulators, okay, and which reduces the execution time of the simulator, and practically it becomes more viable for any application to be executed on this accelerator platform. Okay. So what is the scenario in this architecture, accelerator architecture? So there is a Param cluster, supercomputing cluster, which is Slurm workload manager. Slurm is nothing but job manager. Okay. Now whenever we submit any application task to this particular platform, the Slurm, it will see that which part means we have to offload. So right now it is doing manually, but we can develop this modules which can automatically detect which particular part is computed in time, which part should go to the quantum computer, and which particular part should go to the classical system. Okay, and this particular mechanism is particularly known as offloading. So when we are having a classical system, when we are having a quantum system, main process offload the task. So the offload task is executed on the quantum, and the remaining task is executed on the classical. So based on these particular things, there is an InfiniBand network on this supercomputer, and the simulators which we are having, they are offloading the quantum task on the GPU node, vector node, FPGA nodes, and with this software stack available, this is an open quantum assembly language. There is circuit generation library, and finally it is being converted to microarchitecture, and finally results are being sent to the master node. So based on this architecture, it gives a platform where this quantum task can be offloaded to from a classical task, and this quantum offloaded task can be executed in very less time on a supercomputer based scenario on the quantum accelerator platform. So right now we have seen what are the various applications. We can just see what are the various applications. We can do AI, we can do drug discovery, we can do optimization, we can do cryptography, we can do science, and there are many more. Okay, and there is a platform. This is a simulator platform, and then there is an accelerator platform. Okay, which will enhance the simulator operations. So which means that simulator things can take less time for execution, and all these libraries and software stack are being developed, and they are being integrated into this 3 test bed: GPU test bed, vector test bed, FPGA test bed, and integrated on a supercomputer. Okay, now with the supercomputer stack of this software, it is being integrated. So what we have done, actually, we have done some benchmarks like QSIM benchmark, CPU versus GPU benchmark, and definitely you can see the GPU, it is time is being reduced, and drastic time is being reduced. Okay, so you can see the blue one is a CPU one, and the last one is like a GPU. So various GPUs we have tried, and based on that, you can see a drastic decrease in the execution time is there. Based on this is done by our internal benchmarking, and there are some benchmark by the NVIDIA, because the GPU are being provided by NVIDIA. So they themselves have done a lot of quantum benchmarks. So there is a state vector simulation which is taking 8 minutes. Okay, now the same if we do on a quantum this GPU, it is being executed in 7 seconds. Drastic reduction in the execution time. So this benchmark is available on the NVIDIA website. You can see there. Again, there is a application benchmark like QFT, Shore, and Sycamore Supremacy benchmark. This is by Google. So this benchmark also you can see a lot of gain is there. So the moment we are doing on a normal CPU and the moment we are doing on normal GPU and multiple GPUs, then you see the lot of reduction, lot of speed up is there. Okay. So this shows that yeah, there is a practically proved speed up in this execution when we use the GPUs. Okay. Now, what problem we want to solve? Okay. So there is. So first we have seen the simulator platform, then we have seen the accelerator platform. Now we are seeing a HPC quantum integrator hybrid platform on which the particular application can be executed. What are the applications? We have artificial intelligence, we have drug discovery, we have optimization, we have cryptography, we have financial services. All these applications can be executed on a HPC. Now this HPC platform, they work on the MPI and OpenMP, OpenSSD. These are the various libraries that uses this HPC. So in this classical HPC platform, there is a Slurm job manager which offloads that particular task to the simulator. So this is a QSKIT simulator, QSIM simulator served by Google, a QSKIT by IBM, and this is open source actually, and QSIM by like ISC, where CDAC and IIT Roorkee, they have provided the QSIM platform. And this is being executed on the classical quantum interface, and finally it is gone offloaded to QPU, and this is a scenario of the hybrid task. Okay. Why we are talking of all this hybrid scenario and hybrid tasks and all these things? Because we can see there is a sustainability goal by the UN, and every country has to finally become a sustainable country, and we all have to adopt these 17 sustainability goals. Okay. Now, why it is so important? Because this sustainability that we are talking can be achieved. Some of this problem can be addressed by the quantum computing. Let us see one by one. First, sustainability, when we see number 2, zero hunger. So quantum computer can definitely work on this particular problem with the nitrogen fixation problems. Like there's a MOFE protein on the left and there is a FEMOCO on the right, that will be able to analyze the quantum computing to help the reveal complex chemical system behind the nitrogen fixation by the enzyme nitrogenase. Okay. So what is happening actually? What is nitrogen fixation? Nitrogen fixation, natural phenomena. This is happening by lightning and all those aspects. Okay. And there is a enzyme. Okay. There is an enzyme. And once this enzyme is being formed, nitrogenase, there is an enzyme called nitrogenase. This particular reaction occurs at a very fast pace. Okay. So can we study the molecular structure of this particular complex compound, and that can be definitely usable for the nitrogen fixation. Okay. And nitrogen fixation, nitrogen you can use this all these things are being used for fertilizers. Okay. So whenever we are having a structure, we just pass out to structure generator, it will be optimized. There is an orbital optimization, and then finally we will compute the energy, and this whatever energy is the minimum is the stable structure. Okay. And this is a quantum classical phenomena where this type of algorithm can be used to predict a stable structure, and that is very useful on this things. Second aspect we can see is actually, so this is one of the sustainability goals, zero hunger. Okay. Second, again, we can see in the climate change. So climate change is actually the point number 13, where we all have to address the carbon reduction. All the countries have to address this carbon reduction. Okay. Now there is one chemical reaction that you can see here. What is happening is actually in a catalytic cycle studied in this paper, there's a paper, you can see the reference is given. Ruthenium based catalysts react with the carbon dioxide and hydrogen molecules to produce water and methanol. That reaction can drastically change. It can reduce, definitely it can reduce the carbon footprint. So carbon dioxide is being converted finally into water and methanol. So this type of reactions, if it is happening in the ruthenium, in presence of ruthenium based catalysts, definitely that can do very fast. Now this quantum computer can be used to study this sort of complex structure. Okay. Now why quantum computer means we can see why quantum computer are being used in this, because let us understand this. At the back we have Yeah, this. Okay. So let us assume that when we are having a protein docking, there are various combinations. Okay. When we say docking, it means there is a one protein and there is another protein. They dock with each other and finally they form a minimum energy state. Okay, that minimum energy state we have to calculate. So there are like millions of state. Out of that, there is only one, like we can say, minimum energy state, that is stable state. So all these states we have to go one by one in classical. But in quantum, what we can do superposition of all this state, and one shot we can measure it. Okay, and definitely we have to do some more shot because the quantum is probabilistic. So maybe if we run 100 times, we will get the correct answer in that. So that way, this quantum parallelism can be exploited in these type of applications. Okay, so whenever we are talking of these applications, a carbon footprint reduction, their quantum computer can play a very important role in these aspects of the simulations. Okay. Then there is another problem called good health, drug discovery. Drug discovery, the quantum computer, they have simulated large molecule. They have not simulated very large molecule, but yeah, there is a hope that future drug discovery, whenever the logical qubits are available, this particular quantum, like we can say, quantum computer based applications can be drastically helpful in the pharma industry. Okay. Then we have affordable and clean energy. So quantum battery, okay, it never loses a charge. The battery can work and harness the power of excitonic energy. So these are also in experimental phase. Then there's the energy distribution. Energy distribution is again an optimization problem. Okay, so wherever there is optimization, quantum computer are definitely they can be used. So it can be used in grid cybersecurity, optimization of the heat exchanger, and it can also be done by using customer analysis. Okay. So based on that, in the energy distribution application, quantum computer can be very useful. Okay. Effective vaccine delivery. You know, a lot of efforts are being put in delivering the vaccine when this COVID was there. So this is again a traveling salesman problem. Okay, where we have to deliver a particular vaccine by traveling the shortest path. So this is known as traveling salesman problem. And based on this traveling salesman problem, this optimization can be done by quantum computers. Now let us see why quantum computer is important, because quantum computer can be used in drug discovery. They can be used in an optimization where the simulated path of the can be used. Then it can be used in nitrogen fixation. It can be used in we can say uh, Monte Carlo method. It can be used in the simulations where a lot of engineering simulations can be happening. Okay. So a lot of scientific problem, the quantum can make an impact. And to study this, there is a quantum zoo. Okay. So if you can go and type quantum zoo, then you can see there are like more than 600 algorithms. Quantum algorithm are given. So what you can do, you can go to quantum zoo. There are a lot of associated paper given. There is a lot of associated material given. You can download it and you can develop your own code. Okay. So this quantum zoo is being maintained by Stephen Jordan. And then this is a comprehensive catalog of all the quantum algorithms. And you can see there are more than 600 algorithms available on this. So based on that, I think we can go there. We can see what are those algorithms, and we can implement those code in our simulator platform QSIM. And finally, we can see whether there is some quantum advantage or not on each and every algorithm. Okay, so that is a very very intensive exercise where we go in the quantum zoo, we download a particular application, we write a code, we execute on a platform. So all these things can be done. There are a lot of things to be done. So when we talk about the HPC stack in this uh, parallel processing, we are talking about MPP, we are talking about SMP, we are talking distributed computers, we are talking about network connection, InfiniBand, and those type. We are talking about software programming. So this is a very matured stack. Okay, when we are talking about the HPC stack, this is a very matured stack, and right now all these problems are being solved in the HPC. Okay, but when we talk about the quantum computer, this stack is still not mature. We are still at the assembly language where we have to develop a lot of high-level compilers. We have to develop a lot of high-level languages. We have to develop a lot of instruction set architecture. We have to still the architecture of the quantum processor is still not finalized. Which is the best one? Nobody knows. Okay. So in the quantum computing, still there are a lot of work to be done. This total software stack, interface, control stack, and QPU, that has to be finalized. Okay, and a lot of research is going on in this area, and definitely you will see after some time you will get a matured software stack where this software compilers, transpilers, all these things will be available. But now we can see lot of advantage where we have lot of potential to work in this area. All this is blank. We can start working, and definitely lot of work has to be done. So based on that, there is a open quantum ecosystem proposed, from application to algorithm to framework to architecture to control logic to control plane to quantum plane, where all these layers need to be developed. Application layer, lot of algorithms are there. We need to develop in the code, we need to develop in the application, and we have to develop the optimized circuit for that. Then there are a lot of algorithms there are a lot of frameworks there, need to be developed. Quantum architecture is still not finalized. We don't know superconducting is best, we don't know photonics is best, we don't know neutral atom is best. Then there is a control logic for pulse timing calibration, where this quantum chip actually works on the microwave pulses. Okay, they are not working on like this our electron flow. They are working on the microwave pulses. So based on that architecture, a lot of things has to be done, where this pulse and timing calibration can be done, where this optimal control can be done. There can control plane, there can be quantum plane, where we talk about fidelity, where we talk about gates, we talk about interconnect, and then finally there is simulator for validation of the performance. Okay. So for this actually what we are moving ahead is a HPC quantum integrated computing, which is known as HPC quantum integration, where there is a supercomputer, there is a quantum computer. You can see at the left, they both work together to solve a application to particular problem. And all this application which we have seen, like drug discovery, financial application, they can solve by using hybrid optimized algorithms, and this can definitely go to a lot of advantage, where HPC is there plus the quantum accelerated computing is there, and quantum computer can work as an accelerator to solve this hybrid problems in a like we can say in a time that is we can find the advantage than the pure HPC or the pure quantum job. Okay. So what is this HPC quantum integration? Various aspect we can do. Okay. So suppose the HPC is consisted of compute nodes. There are various compute nodes. There is a GPU, there is FPGA, there is PCI Express is correct, and there is an interconnect network known as InfiniBand. Now, when we are connecting this to accelerators on quantum computer, so this is like a quantum computer which is having control electronics, which is having dilution refrigerator, which is having quantum processor, and this can be connected. Now, technical use cases are actually optimization, where QAOA based algorithm, VQE based algorithm, this type of hybrid particular jobs can be executed. So the QPU exists independently in a separate entity, which can be used as accelerator to HPC. QPU is connected through HPC through high-speed network connectivity, and open quantum architecture based on the QPU that will be modular, submodular can be used. Okay, so based on this particular work, we can see that there can be a offloading mechanism where the CPU workload and the quantum workload can be separated at the job manager level, which is at Slum level, at the schedule level. That also can be separated at the runtime level, where the CPU task and the quantum task can be separated. And finally, it can also be done at the functional library at the code level, where the master function can be having sub-function, whereas there is a quantum sub-function, there is a classical sub-function, and then finally aggregator function. So all this bifurcation and information actions can be done. And finally, all this quantum job can go to quantum, classical job can go to classical, and this is being executed. So this is how we can see HPC quantum, all this executed in a synergy finally to solve a problem. And all those problems we can see are like applications that we are observing. Okay. So when we say HPC quantum integration scenario, where there will be a host supercomputer, there will be an operating system, there will be quantum QPU driver. Those QPU driver will take care of the QPU, and from classical to quantum, all these jobs can be executed. And this is known as hybrid algorithm, where classical and quantum computation can be done simultaneously, and this total system can be available on the cloud. Okay. So this is what we have seen recently. So this quantum classical interface, how it should be there? We can see that whenever there is a quantum plane, there is a classical plane, there is a control readout mechanism, which is routing is there and readout is there. So based on that, there is a pulse to digital and digital to pulse level conversion is being done. And there this quantum classical interface plays a very important role, where all these microwave pulses are being converted to digital signals, and these digital signals are being converted again back to microwave pulses. So these are the particular phenomena, is very important phenomena that is happening in the quantum computation task. Okay. So that's how this HPC quantum integration ecosystem is being developed, where we reformat the problem, we identify the quantum component of the HPC application, and we do optimize by code profiling. We do problem decomposition. We divide the problem into quantum and classical module. We recombine the problem domain, code integration using the offloader. We also do the job scheduler integration. We are integrating of a hybrid quantum classical code with a job scheduler. Finally, all this will result in a solving a particular quantum or solving a particular problem in a, what we can say, in a time, okay, which is also near to real time. Okay, the problem with the optimization is that we need real time solutions. Can we do it faster? Can we do it in a very less time? So based on that, this particular quantum computer can work as an accelerator to solve this sort of problems. Okay, so this is what we are proposing, that there can be reference computing ecosystem development with lot of quantum applications. Okay, when we are saying problems, the problem are neither quantum nor classical. Okay, so this problem are grand challenging problem that need to be solved, and based on the classical as well as the quantum computer, or as a combination of classical and quantum, we need to solve this particular in a real time scenario. We need to solve them. Okay, then only they can have some advantage. We cannot solve like a drug discovery problem in COVID when there are like COVID is already gone. Okay, so we have to see whenever any epidemic and any situation comes, we should be ready with the real time computational framework which can solve these applications, which can solve this problem, which can develop this application, we can execute this application on this reference computing ecosystem, and can give the result in a real time scenario. Okay, we can't wait for 1 month, 2 months for a particular problem to be solved. So based on that, whatever R&D community gives the outcome in the form of tools, technology, and there is an industry-oriented application development like life science, drug discovery, protein simulation, quantum-enabled machine learning, aerospace optimization, automobile sector, financial sector. All these applications with the international scenario of the code development, which can enable India to participate in global hybrid classical quantum system, and India to be a part of standardization body. A lot of standardization is being remaining in this. Okay, so we ourselves are a part of BIS, but lot of standardization aspect has to be developed. And then finally, we are giving a reference facility which can test, validate the quantum processor technology, dilution refrigerator, and we can execute all this in the form of cloud. All these access are being given in the form of cloud. So finally, the impact is actually we foster a quantum ecosystem for Indian startup, industry, research community with a reference facility investors based on superconducting based quantum computer architecture. Okay, so this is the total scenario of executions. So what we are seeing here is actually we are providing a platform. There are problems. The problem has to convert it to some application scenario. Those applications, there is a coding required. That coding has to be based on the quantum gates. Either it can be done by automated gates, or it can be done by manually, or generally Python framework is being used. And based on this execution platform, this particular quantum job can be executed either in a pure quantum way, or in a pure classical way, or in a hybrid way, where some part is accelerated by quantum and some part by classical. And that division can be done at job manager level, that division can be done at a runtime level, and that code has to be developed particularly on that way. Okay. So this gives a scenario where we are talking about the reference computing ecosystem development with all the applications. So when we talk about CDAC is under the Ministry of Electronics and IT. We focus on the hardware, electronic systems, and software. We develop co-development is big industry and academia, and we evolve the technical milestone in the market, and then we solve this problem statement use cases from the end user agencies to find a solution to a particular problem. Okay, so now what we can see in India, Lot of quantum talent is there. Lot of quantum talent is there. You can see students, lot of students, they are participating in hackathons, they are participating. The maximum number of, like, which you can say IBM quantum computer users are from Indian. Okay, so this is being like figure given by the IBM itself. So lot of talent is there in India, and that talent, as per the McKinsey report, India is the highest talented country in quantum. We can see Europe first, but Europe is not a country; it is union. So India is like a highest talented country, where a lot of students, lot of people, they have interest in the quantum computing. They are doing lot of work on the IBM platform. They are doing a lot of work on like our QSIM platform we have done. So in India, what we require is actually we have to provide this ecosystem that we have talked. So we have to give a reference computing ecosystem development to solve these particular applications. So these are the particular platform we can give. These are the particular stack we can give. Finally, the main purpose is to solve these problems. We have to solve these problems, applications. So these are the applications in the area of quantum computing, which touches the each and every aspect of our problem solving environment. So artificial intelligence, drug discovery, optimization, cryptography, financial services, lot more, but majorly focusing on the optimization. These are the applications that need to be solved by using quantum computing. So we see a lot of talent there in our country. Our country needs a platform like this. Our country needs algorithm development. So based on that, this particular uh, we can solve a lot of problems. We can develop a lot of application, and definitely we can be again a IT superpower in the quantum algorithm also. You can see India is a, like we can say, a software superpower, where a lot of service industries there, like in India in IT sector. Similarly, in the quantum also, we can use the technology talent. We can give a platform, and we can develop uh, a pool where we can have a lot of application developments in our country. Okay, so there are a lot of opportunity in the quantum computing. Quantum computing can make a huge impact in addressing various grand challenging problems like drug discovery, artificial intelligence, cryptography, financial modeling, weather forecasting, every aspect wherever there is optimization. Quantum computing. So quantum computers are not good at 2 plus 3 arithmetic operation. They are used for some particular class of application which are generally optimization problem. There are various candidates for the quantum computer like superconducting, ion trap, NMR, lasers, Q dot, moleculars, and lot of platform which are not yet finalized. There is a no winner here. We are lot of research is being done in each and every implementation methodology of the qubits, but there is a no, we can say, winner or no finalization of this technology where the QPU implementation can be finalized and standardized. Okay. And a good quantum computer that can provide a new computing power, opportunity, curiosity to solve many problems. And some of the quantum applications are integer factorization, quantum magnet simulation, cryptanalysis, machine learning, supply chain optimization, robotics manufacturing, computational material science, alternative energy, and this can come up. Quantum computing can come in a huge way to solve this sustainability, to solve this or to solve the sustainability goals, to achieve the sustainability goals of the UN, that are the major aspect that is being discussed. Okay. So with that, let us develop a quantum ecosystem in our country with scientific research. We have to develop quantum algorithm repository. We have to use the platform like quantum accelerator, hybrid quantum computing, HPC quantum integrated platform. We have to come up with the industry standards. We have to develop the education and training framework, and with simulators and interfaces, we have to come together. We have to break the silos. We have to collaborate, and we have to succeed together. Thank you.
Thank you, sir. Participants, if you have any queries, questions, please post your question in chat box, or you can unmute yourself and ask your question. Sir, there
Sir,
is a question in the chat box from Yasmin ma'am. Could you please discuss about quantum technology with cyber security?
Yeah, so when we talk about this, mostly when we say quantum computer, still it's very infancy. we are talking about a lot of things, but yeah, it has theoretically a potential. When we see prime factorization, so definitely Shor algorithm is there, which can do the prime factorization. It can break, it can has have a potential to break the encryption code, RSA codes. We generally see lot of Chinese paper, they come up and suddenly disappears. They claim that they have broken this and they have done this, but finally all these are claims. And right now we are not finding any real practical, what we can say, evidence where this is being done. And when we observe it, generally it requires like millions of qubit in when we say Niskera, and then we talk about fault tolerance. So there are a lot of estimation which are far beyond this com- current compute capability. So this still a far thing, but yeah, theoretically it is possible. We never know which quantum computer can come, and which we never know which algorithm can be developed. And but there theoretically it has a potential to break this, and there's a security threat, and it can totally finance sector can be like distracted in this way. It has a huge impact. That's why all these defense agencies are being investing huge on quantum computing. If there is any chance, it can do. And China is like heavily working on this development of this type of things. So yeah, there is a threat, but yeah, then there is a post quantum cryptography application. So based on cybersecurity right now, we need not worry, but we have to be prepared for the future. That is the aspect we can say. Thank you.
So can you share your mail ID, please?
Yeah. So I think this is a very late night session, and you all are like maybe since evening you are all attending. I don't know, you are at your homes or your college, but I have seen this really lot of FDP happening, and I have got like call from many FDP. So really see a lot of enthusiasm in you people sitting late night attending these sessions. I have seen a lot of enthusiasm in you people. So it's really good for our country that if our faculty are so enthusiastic, they can develop a good student force, and we can be a quantum superpower with this national quantum mission, as well as whatever efforts we are putting. Definitely, we are not up to the mark. Like we can see the difference. We have 6 qubit. IBM has developed like 1,000 qubits, but we have started this, and IBM is working since like many years, maybe 20 years it is working on this technology. So we have started. Definitely, we will be able to cross that scenario where we will be also be having many number of qubits, as well as we focus on this HPC quantum integrated scenario, which can definitely give us an advantage. Yeah.
Thank you, sir. Participants, is there any query? I think there are no questions. Radhika ma'am, you can go
Yes,
ahead with
ma'am.
the session.
Yes, ma'am. Thank you. First and foremost, we extend our heartfelt thanks to Mr. Amit Saxena, sir, whose insights and expertise have illuminated the intricate world of quantum computing application areas. His insights have helped us to understand its impact of quantum computing. His simple and engaging explanations have made it easy to see how this technology can be used in different fields. Sir, please accept our virtual token of appreciation.
Thank you. Thank you so much.
Thank you,
It's a
sir.
very nice opportunity, and hopefully we can also meet sometime in a workshop physically, and we'll discuss more on this. The quantum community is very small. We all know each other, and we keep on conducting some workshops. And definitely, I think in your college also we may do some workshops. So
Yes, sir. Please give us the
Yes, sir.
opportunity to conduct the workshop. We'll definitely invite you. Thank you so much, sir.
thank you. Thank you so much.
We would
Thank you.
also like to acknowledge and express our thanks to all the attendees. Your presence has made this session all the more meaningful and memorable. Thank you all, and we will meet again at tomorrow's session at 6 p.m. Thank you and have a good day. Attendance link for both the sessions are given